Yes, welcome back to Galantis Academy. How are you doing today? And I hope you're doing well. Alright, so in today's lecture, in today's video, we'll be discussing elasticity, more or less the simplest topic in physics. Right, so we are going to, in today's video, we just talk about the theoretical aspect. Yeah, the theoretical aspect, building the foundation. Right, building the foundation. In subsequent videos, most of us will be treating our questions to solidify your understanding on this topic. Is that clear? All right. So when they say elasticity, what comes to your mind? First, when you say elasticity, we should know that we are referring to what? Something being elastic. The elastic property of an object. So whenever we say elasticity, we are actually referring to what? The elastic property of that object. Now, to define it, you can say elasticity is defined as the ability of a material to resist deformation and spring back to its original shape and size when deforming force is removed. Right? So it's just simply the ability of any object, right, to return back to its previous state after the distorting force has been removed. Is that clear? So let's assume this. I have a rubber band, let's say a spring, for instance, which is of this size, right? But due to the force which I'm applying, it kind of increased, right, up onto this size. Now, if I want to confirm if this spring is actually elastic, after removing the distorting force, I expect it to return back, right? I expect it to what? To return back. I expect it to return back. So what will happen is that all this will go out, right? Going back to its previous state, right? That's what elastic materials do. Do you get that? And if you look around, elasticity comes to play in our everyday life, even while we are playing football and the rest. If the football, right, does not have elastic property, it will be very hard for you to enjoy playing football, because once you bounce it, it will more or less stay at that position. Do you get that? All right. So one of SI units, we've been told countless times that most quantity in physics actually have SI units. Now, elasticity, does it have units? Are you sure? Okay, depending on the angle you are seeing it from, right? When we are considering elasticity literally, right, it does not have SI units. We are considering it literally, but due to the fact that it actually have an inherent property which have an SI unit, which is elastic modulus, right? Elastic modulus and elasticity are very, very, very related. I can say, due to their relation, we can use it interchangeably and say, okay, the SI unit of elasticity is what? Pascal. I get it. Or anything regarding what? Pressure. Why do we say so? The reason for this is that whenever we are trying to check the elastic property of an object, right, or a material, what are we doing? We are literally applying force. This force we are applying is connected, or is in relation to an area. So having force and area gives us result to pressure. I get it. So we can now say the SI unit for elasticity and elastic modulus is what? Pascal. Do you get that? All right. All right. Quantifying elasticity. In the previous slide, you now know that elasticity is basically the property of an object. Now, how can we know how elastic an object is? How can we know that, okay, this is more elastic than this? Okay, this is expected to do this. This is not expected to do this, right? Regardless of how passionate you are about football, you cannot play with stone. You cannot kick stone and say, okay, since football is not available, I'm going to use what is at my disposal, which is stone. It doesn't work that way. I get it. All these things which all the judgment which we make in our everyday life are actually arbitrary, right? But now we are now adding value. We're now attaching a numeric value to what? The elasticity. And the various way to calculate elasticity is through stress. Another is through strain, and by examining the stress strain curve. Is that clear? All right. Now, first one is what? Stress. When you say stress, what does it mean? It's not the normal stress that almost school is stressing me. No, not that one. When you say stress, right, it's simply the measure of the internal forces within a material resisting deformation. Forget that big grammar. I will explain it. All right. Now, let's assume we have a tube here. Right, a tube which can stretch, right, which is capable of stretching, right? All right. So after stretching, okay, let's say in absence of stress, right, that it can stretch up onto this part. Right, it can stretch up onto this part, right? Even this part can stretch up onto this part. But it is this stress, right, that limits the way an object stretch. I get it. That's what they said here is the internal force that resists. I get it. That resists deformation or that resists stretching. So in the presence of stress, I expect it to be like this. Instead of this part, right? I expect it to be like this instead of this. I get it. So the more the stress value of an object, right, the lesser is it able to stretch. I get it. And literally, stress is actually a combination of both force and area. I get it. Remember that force will be acting in this direction. That I'm pulling you to my two hands. I get it. And there is a particular area which it is acting on, right? The particular area which it is acting on, right? So if a force is applied uniformly on this on over a surface area, let's say the surface area of this is A, right? While a force F, I get something like this. Then the stress is actually F. Stress is simply equal to force over what? Area. Do you get it? Now we have to know the SI unit too. What's the SI unit of force? Newton, right? What's the SI unit of area? Meter square. Okay? Put it on the horizontal part. We have Nm raised to the power minus 2. Is that clear? Alright. There are three basic types of stress. The first one is longitudinal stress. The next one is volume stress, which can also be known as bulk stress. The last one is tangential stress or shear stress. Now, I appreciate them for using a very, very simple term in categorizing it. I get it. So by understanding the English words, the terminologies used there, we can have an idea of what each type of stress is trying to address. For the first one, they said longitudinal stress. So longitudinal stress will definitely be along the length. will definitely be what? Along the length. So if I'm to hold it, let's assume this is my finger now. I'm trying to hold it, I'm pulling it right in this direction. I'm holding this one too. I'm pulling it in this direction, right? The force resisting this deformation, right, in this direction, in this particular direction, right, is known as what? The longitudinal stress. Now, what do I have here? I said the longitudinal stress refers to the stress experienced by material when the force acts parallel this parallel, right, parallel to its longitudinal axis. Is that clear? Which is essential its length. The key aspect of longitudinal stress is the direction. Now, if I'm applying force in this direction, that's not longitudinal stress. In this direction, that's not longitudinal stress. Are you getting? So my orientation matters a lot. It must act along the length of the object, as opposed to pushing. So alright, so that's just it for longitudinal stress. So classification of longitudinal stress. Okay, I failed to mention something here. Look, it can be pushing, or okay, no, not that, as opposed to pushing or squeezing it perpendicular, what I just explained here, right? So now longitudinal stress can be divided into two, right, which is, or can be classified into two, which is tensile stress and compressive stress, right? Compressive meaning is acting in opposite direction, it's acting in this direction, like they are coming towards each other. I guess it's just like a ball and this, they are trying to hit each other. That's compressive force. I guess, but tensile stress or tensile force is different in that this is acting this way, right, and this is acting this way, right, in totally opposite direction. Exactly, they are going farther away from each other. Now, tensile stress, this occurs when the force tends to stretch or elongate the object. So if I have a box here, and after applying stress, right, it now have this shape, right? This is what acted here was what? Tensile stress. But now if I apply force, and after applying force it becomes more or less smaller, right? It becomes more or less smaller, something like this, right? What came into play, what played out here was what? The compressive stress. All right, the next one, volume stress. So this is simply the stress experienced by an object in all dimensions. So if I have a box now, my drawing, so let me draw it again. So if I have a box and I'm applying force this part, I'm applying here, right, I'm applying here. In short, in all directions, if I'm applying it on this box, what this box will experience is known as what? Volume stress. Volume stress can also be regarded as, or be known as, bulk stress, right? So one thing you have to take away from this volume stress is that volume stress affects all dimensions, right? So both in this direction, that is this z direction, which I can't really demonstrate well, I get it, right? So it affects all dimension, and it can result in either compression or expansion of the object. Now if I was acting in this direction, right, you expect it to expand, right? You expect it to expand. But if I was acting in this direction, you expect it to what? To be compressed. Is that clear? So get it right, get it well. Next one is the tangential stress. Now this kind of confusion, right? This kind of confusion because it's more or less related to longitudinal stress, but they are different. So different. Okay, now you know from circle, when you say tangential, it's something that just crosses the surface. It crosses the surface, right? It just crosses the surface, right? That's what tangential generally means. I get it. Now, what do you notice here? Tangential does not put into consideration the length, unlike longitudinal stress, which categorically stated that it must be along the length, it must be parallel to the what, to the material experiencing the stress. But in tangential, I can have it this way, right? I can have it just crossing the surface, right? I can have it pulling both of them together, right? I can have forces pulling both of them together. So that's tangential stress, right? It's also regarded as shear stress. Now, shear stress means something tearing apart, right? So tearing apart. So that can be a clue for you to differentiate between tangential or shear stress from what? From longitudinal stress. Is that very, very clear? Right? So it arises from a force applied tangential to the surface rather than pushing or pulling along the length, just like in longitudinal stress. Now, stress calculation. Though I've stated this before, that stress is equal to force over area, right? I've stated it over and over again, right? Now, this symbol here is a symbol for stress. So instead of me writing all this, I can just put it this time, right? Something like this. I guess as simple as that. So the F there is measured what? The F there is measured in. The F there is measured in Newton. A is measured in meter square. You know, remember area, length times breadth, meter times meter, then meter square. Good. So area is measured in meter square. So what we have here is nm minus 2, right? So that's the SI unit of stress. Is that clear? So please take note of this, right? Take note of this. Take note of the formula and everything. All right. The next one, strain. Strain is easier to understand because strain is more or less like a relational quantity. We are trying to compare, okay, the previous state of this object and the now state of this object. How can we differentiate it, right? What is actually what changed, right? So strain is literally the measure of the relative deformity or deformation experienced by the material. Is the relative deformation experienced by the material. Now let's assume I have something like this. Which original shape is this? But due to applied force, it's now become this way. From here to here is what? The extension, right? Good. While from here to here is what? The original length, which I can add as L, right? So from here to here is what? L plus E. Exactly, that's the total length now, right? L plus E. Most likely, most times, we don't know the extent of the extension. We don't know the dimension of the extension, right? So we have to employ strain to get the job done for us, right? To get the job done for us. Okay, just like in stress, when we say there is longitudinal stress, there is volumetric stress or bulk stress, right? In this part now, I cannot tell you, oh, length must be, whenever I'm talking about length, that's when strain comes into play. No, I get it. We also have in this strain, we also refer to length, we can also refer to volume, right? We can refer to both of them. I get it, right? So since we're talking about ratio here, right? Since we're talking about ratio, because it's actually expression of the change in dimension. Let me put it as D over the original dimension, right? So this kind of ratio, right? If here was to be meter, if this D was to be measured in meter, and the initial dimension was also to be measured in meter, then it will cancel out each other. So you can see that since it's just a ratio, it has no unit, right? And therefore it has no dimension, right? So stress is just like what I've stated here, is what? Change in dimension over the initial dimension. So type of strain. It is classified into there are three types of strain. Basically, three types of strain. Right? One is the longitudinal strain. Next is volume strain, shear strain, and tangential strain. Right? So longitudinal strain is literally the strain experienced, right, when there is a longitudinal stress. Right? So I'll come over again. Longitudinal strain is the relative deformity experienced by an object, right, in relation to the longitudinal stress. So longitudinal stress causes longitudinal strain. So yeah, like, is it clear like that? Longitudinal stress causes or results towards longitudinal strain. Remember, strain is talking about the deformity. How much have this thing changed? What is the extension, right? So if I'm applying stress on the longitudinal part, where do you think the extension will happen, right? Where do you think the extension will be more prominent? Definitely in the longitudinal aspect of it. I get it. So I said it here that longitudinal strain refers specifically to the deformation a material experience along its length in response to what? To longitudinal stress. It is a measure of how much the material length has changed. So related to the original length, right? So just like what I have in the other part. So this would be L plus E, right? Minus L, right? So the total length minus more or less like the initial length over initial length. Is that clear? So change in length minus Li. So I can also say here Lf minus Li over Li is what? The strain. Is that clear? Alright, the longitudinal strain. More specifically, the longitudinal strain. Alright, volume strain is actually the strain experienced by an object due to what? Volumetric stress. So this is the strain caused by volume stress. As simple as that, right? So if we have a cylinder, right, and I'm applying a force here, I'm applying force here, I'm also applying force here, I'm applying force here, and on the z-axis I'm applying force, right? You notice that this stuff will not only, the strain experienced by this cylinder will not only be in its length, will not only be in its area, because this is more than this one, this two, this three. So because it's 3 dimension, it will what? Also include what? The volume. Is that clear? So we call it what? Volume strain. So expanding this formula, we have Vf minus Vi over Vi. Is that clear? Right, that's volume strain. Alright, tangential strain. Tangential strain is also called shear strain. I get it. So it doesn't have, now whenever you hear tangential strain, it does not have a specific orientation. Okay, it must be in the longitudinal aspect. Okay, it must be in the horizontal aspect. No, I get it. It can act in several directions. So just say you have a ball and it's acting in almost all the direction I have, right? Almost in all the direction, right? That's when we have tangential strain. So tangential strain, which is also known as shear strain, describes the deformation of a material due to what? Tangential stress. And this is formula is represented by this, right? So right, this x over LO, right? You should know by now that this is the initial, so I can also put Li here, right? This the displacement, right? Knowing that it can act in all directions, so we can actually resolve it. Okay, talking about the one that is the upper part of it, and the lower part of it. All right, so the upper part of it, how well does it expand? Okay, the lower part of it, how well does it expand? So that's why this figure, what we are seeing here is actually the displacement of the upper layer related to the what lower layer, while this the original distance between the layer. So before applying all these forces, there was a constant force, right? There was a constant distance, I mean to say, right? There was a constant distance between here and here, constant distance between here and here, constant distance between here and here. I get it. All right, so that's all for tangential strain, right? Stress strain curve. Now this is a particular curve or diagrammatic representation which you should familiarize yourself with always and every time, right? Because most examiner might just bring out the curve, right, and say, okay, mark a particular point. Okay, what does this signify? What does this mean? Right? So I'll explain it. Now, first of all, what does stress strain curve mean? Right? Why is it important? Why should we even know it? Right? So the relationship between stress and strain of a body is often depicted by stress strain curve. Like now, this is very important when building bridges. Okay, now if we apply this force, okay, what are we expected? What's the change in length we're expected to have? Instead of being practical in everything, this gives us a very clear understanding of what our outcome is expected to be. I get it. So this curve provides valuable insight into the elastic behavior of the material. Alright, so this is how the graph looks like. Right, this is the stress, strain. Are you getting? Alright, so we can have, first of all, we're going to have a very straight line, right, to demonstrate Hooke's law. I'm coming to that, Hooke's law, right? So this point here is known as what? Proportionality limit. Proportionality limit. So in this point, right, the said material or the material in question obeys Hooke's law. I get it. It obeys Hooke's law, though it's still elastic. But beyond this part, right, it does not obey Hooke's law because it gets curved, right? This new point here is known as the elastic limit. Elastic limit. I getting the elastic limit. So between here and here, all this part, this object is still elastic. That is, even at this point, if I release that object, it will return back to its original shape. This point, which is signifying 0, is the point in which no force is being attached. But when I apply force, it reaches here, and if I keep on adding force, you see how the graph go. I get it? So it slopes downward a bit, right? So this new point is known as the yield point. So yield point is like, oh, I can't bear it anymore, right? And beyond this part, several things start happening. It loses its elasticity almost completely, right? This point is the breaking point, right? You can experiment this using a rubber band, right? The breaking point, right? It starts shattering, right? And the last part is the final point, right? So it fragments. That's the fracture part. Alright, so these are what you should know. You should know for a must in any exam which you be preparing for. I get it. As you can ask the fracture points. I hope you guys noted this. They can point a place and say, okay, all right, guy, what does this mean? What does this mean? Right? You should be able to describe it. All right, let's go by it again. This proportionality limit, right? Throughout this point, Hooke's law is obeyed, and the slope of this graph gives the modulus elastic, right? The elastic modulus, or modulus elastic modulus. It gives it that, right? So this point is the elastic limit, right? Beyond this point, this object, when released, will not return to its original shape. Right? This is the yield point. Right? This is the breaking point. It starts shattering, and the fracture. It can, no remedy. Right? No remedy. I can just represent it as slightly dotted point. Is that clear? All right. So let's have a recall. All right, because I was a bit fast. Now, what I mean by proportionality limit. Now, the limit in which the Hooke's law is valid. I hope you remember that. The limit in which the Hooke's law is valid, and the stress is directly proportional to strain. So in that first point, right, between all these parts, the Hooke's law is obeyed. Stress is directly proportional to strain, right? Good. But after it crosses here, this point curves a bit, we now have the elastic limit. The elastic limit is the maximum stress, which on removing the deforming force makes the body recover its original state. So if I have a body now and I leave it at this particular point, then it will return to its original shape. So if it's were to be this size, it will return to this size. I guess. But beyond this, then several things start happening. Right? Beyond the after this we have the yield point, right? So this is the point beyond the elastic limit at which the length of the wire starts increasing. So if you notice, if you are drawing a rubber band, right, after some point you notice that it can't resist that deformity that is happening. It just allows you to do what you want to do, right? It almost looks like plastic. So that's the yield point. That's the point beyond the yield point. Is that clear? Right? So the breaking point, that's the point that I'm like, oh, I can't take it anymore. All right, fine. I'm going now. Right? And it breaks off. So that's it for that. All right, so Hooke's law. What do you understand by Hooke's law? Now, I like keeping things simple, right? Now, Hooke's law states that the change in length E of an elastic body is directly proportional to the applied force or load, provided that the elastic limit of the body is not exceeded. So this is the change in length. So now we're going to get the formula for Hooke's law without cramming anything. Don't cram. Proportionally, right? Force. So he said that force is directly proportional to extension. That's what this formula is trying to tell you. That force is directly proportional to extension. Now in mathematics, whenever we have something like this, we must definitely introduce the proportionality constant. Exactly. In Boyle's law, that comes into play in everything, right? So the proportionality constant which we are going to introduce is represented as K. This K is actually the force constant. This K here stands for force constant. The F stands for force. The E stands for what? Extension. You should know that by now, right? Okay, so this force is measured in Newton. This is measured in meter. Extension meter. All right, so what will be the SI unit of force constant? Simply make force constant substitute the formula. We have F over E, right? So F is what? Newton, and the extension is meter, right? Equal to Nm minus 1. Is that very clear? So that's all about Hooke's law. Now, your modulus, right, which most examiners like asking, is denoted by Y, right? Not exactly Y, more or less something like this. But if you write this, you should still be correct. So it's defined as the ratio of the tensile stress to the tensile strain, right? It tells you how much a material will stretch, right? Okay, we have a book. How much can this book stretch? The only quantity or the only property that can answer that question is the Young modulus. It tells you how much a material will stretch or compress when a force is applied in straight line, right? So I told you is a ratio of the tensile stress over the tensile strain. Is that very clear? right? So this is exactly what you have to find out, what you have to know. But now we're not stopping here. What is the SI unit of what? Young modulus, right? What is the SI unit of Young modulus? First, let's break it down. Stress, if you remember, is equal to force over area. So force is what? Newton. Area is what? Meter square. So we have Nm minus 2. Right? What of strain? Strain is what? Extension over length. How do I know the extension? Okay, remember that I said that this is like L plus E, then minus L, right? Good. This is the initial. This is the initial. So if this cancels this, what is left? Only E. I get it. So that's why it equals was extension over length. Now, this extension over length, what would be the SI unit? Extension is measured in meter. Length is also measured in meter. So this is what? Dimensionless. Strain is dimensionless. Is that very clear? Alright, so if we know that this is dimensionless, right, what of this? We just put our N M minus 2. So the SI unit of your modulus is N M minus 2. That is Newton per meter square. As simple as that. The last part is the work done. Right? The work done in spring and elastic spring. Now, there is to tell you how I arrive at the formula, which you'll be seeing very soon. You have to go through calculus, and I'm sure not everyone here offers mathematics, so I'll just put in very simple. The work done on a spring is the energy transferred, right, to the spring when it is compressed or stretched. Now, if I compress something like this spring, right, it will most likely be like this. I guess if I release it, I get it will spring back, right, with force and even exceed this point. I get it. So that is the stored energy in it. The stored energy. Do you get that now? So if an applied force cause an elastic spring of original length L to undergo an extension or compression, just like what happened here, it undergo compression first, then extension. Right, it exceeds the initial length. I get it. Then the average force, since we're talking about compression and then extension at the same time, I get it. Then the average force will just be like F is equal to right F2. So the average force will just be like C plus E over 2, something like this. I get it. But since we're talking about extension force now, right, I will represent this as this, right? I will simply just use 0 plus F over 2, which is equal to what? F over 2. Is that very clear? Right? So that's the average force, right? So just forget about stuff. So the average force will just be like this, F over 2. That's the force experienced here and the force experienced here. The average force is F over 2. That's force over 2. I get it. Now, remember, recall, work done is equal to force times distance. So now, force is what? F over 2. That's our new force. That's average force, right? So what of distance? The distance is the extension, right? Something like this, right? Good. So the average force, I just put this here, so it's something like this. So I can just say the work done is also equal to 1 over 2 Fe, right? 1 over 2 Fe. But sometimes, what if we're not given F? What if we're not given the force directly? What are we to do? What are we expected to do? All right, remember that according to Hooke's law, we have F equals what? Ke, right? Remember this. Just put it into this formula. We have 1 over 2 F, that is, replace this F by Ke, right? So we have in bracket we have Ke, right? Then add your E at the end, right? This and this are similar, so we can just have 1 over 2 Ke squared, right? So something like this works out. Something like this what works out. So now, if you are asked to find the work done in spring or elastic spring, the only formula you have to remember is 1 over 2 Fe or 1 over 2 Ke squared. So this is the only formula you just need to remember, right? Is that very clear? Okay, now let's have a recap. Now, elasticity, you know that already, right, is the property of an object itself, right? Stress, is experienced by almost all objects, right, and is the inherent force that prevents deformity. Strain is just relative. Okay, let's know how much this object in question has extended, has been compressed, right? The stress strain curve, where we can see the proportionality limit, right, the elastic limit, the yield point, the breaking point, and finally the fracture point, right? Hooke's law, you know that by now, that is directly proportional to E, right? So, and the proportionality constant is known as force constant, right, which is K, E, right? Young modulus is simply the ratio of stress to strain. It's simply the ratio of tensile stress towards tensile strain. Let's wrap things up. The last one being work done in spring. I just explained that before this particular slide, that one is 1/2 force times extension, or in a case whereby you're given force constant, it will be 1/2 K E squared. That is K meaning for standing for force constant, and the E standing for extension. Right, so exactly what is represented in this place. Okay, thank you so much for staying with me up until this moment. Expect another video. Expect another video where we're treating questions starting from the simplest, the simple one, expect you to know, then ascending into the more advanced questions, right? Thank you for watching, and share, subscribe, and share, you share to your friends, right? Like, if you have any questions, if you have any suggestions to make, kindly utilize the comment section. Thank you so much. Goodbye.